All right, everyone, here's our last video for this day of the Chapter 8 lecture. We'll have one more set of videos for Chapter 8 when we get into the Clausius-Clapeyron equation. And in preparation for that topic, I just want to revisit this issue again, where when we have phase transitions, we're actually adding heat without increasing the temperature during the phase transition. Pretty soon we'll be taking a look at different types of phase diagrams, for instance ones that include volume in addition to pressure, or maybe that include temperature as well. So considering these phase transitions where we have an addition of heat without an increase in temperature, remember we said that's because while the kinetic energy of the system is remaining constant, and therefore constant temperature during that phase transition, what's really changing is the potential energy of the molecules coming further and further apart from each other in moving from the liquid to the gas phase. Now, this last topic I wanted to talk about is a very interesting one to me because it is possible to have multiple phases within a single state. An example we mentioned already was that there are two liquid states for helium. Here is the pressure-temperature phase diagram of water. Notice that the pressure scale is logarithmic, but the temperature scale is still linear. Now, the form of ice that you're used to exists right around this pressure right here, because that is the pressure in pascals that is approximately the standard pressure. In fact, that X right there is the location of the standard state, about 300 Kelvin, and right there is about 10 to the 5th pascals, which is the standard state. So ice 1 is this whole region right here that I've kind of boxed off. But then if you get ice really, really cold, the most thermodynamically stable form of it is indicated right over there with that symbol Xi, which is 11. So if you get ice really, really cold, below 100 Kelvin, then the most stable form of ice is actually ice 11. And then if you ramp up your block of ice to a really high pressure, like right up here, it looks like we're at tens of thousands of atmospheres, then it can convert to ice 2. And then there's a tiny little region of the phase diagram where it's ice 3, so on and so forth. And so you can see where all the different forms of ice are. Now, if you've read the book Cat's Cradle by Kurt Vonnegut, then you may know about ice 9. Now, ice 9 in Cat's Cradle was a form of ice. It's a science fiction book. It was a form of ice that catalyzed the formation of more ice 9 and was also thermodynamically stable at standard temperature and pressure. So therefore, if a little block of ice 9 fell into the ocean, it would catalyze the formation of more ice 9, and it was just a matter of time before the entire ocean, as well as all the streams that flowed into it, froze solid. And then it was only a matter of time before that went into our bodies and just converted all the water on Earth into ice 9. So it was the premise of that science fiction book, but of course ice 9 doesn't actually have those properties, but I think personally it's very interesting that ice 9 does actually exist in real life. Thankfully, like I said, it doesn't have the properties in that science fiction book, but I just found that very interesting and entertaining. But as you can see, there are multiple different forms of ice spread across that phase diagram. Another example of this would be carbon. Carbon has multiple different solid phases, including diamond and graphite, and each one will be thermodynamically stable depending on the ambient temperature and pressure. Okay, so to review what we talked about on this day of the lecture, we saw the pressure temperature phase diagram. Again, tells us the phase at a particular temperature and pressure. We saw how those phase transitions, at least in terms of temperature, depended on the increasing entropy as we transition from solid to liquid to gas. We saw how boiling point elevations always occur as a result of increases in pressure, but freezing point elevations or depressions depend on whether or not its solid phase has a higher or lower molar volume than the liquid phase. And so if you're still unclear about that, make sure you review which is which so you can keep them straight. And then we also saw how there are multiple solid phases potentially, and even also liquid phases. The example I told you was ice 9. One more example that I'll leave you with is chocolate. There are actually multiple different phases of chocolate. And your favorite kind of chocolate is chocolate 5. And if you've ever left a piece of chocolate in a cabinet for a long period of time and you come back to it, it's all crusty and nasty and doesn't taste very good. Well, that's because it phase transitioned to a different solid phase of chocolate that doesn't taste as good and doesn't have quite the same positive qualities as chocolate 5 does. So anyways, that's where I'll leave you with today, and I'll see you on day 2 of chapter 8.